Hello everyone. Today I am going to discuss about Compton effect. In the previous lecture, we had a discussion on photoelectric effect where we found that electrons absorb electromagnetic radiation in the form of packets of energy called photons having energy is equal to Planck's constant multiplied by frequency of radiation, and it gave us the idea of particle nature of light. Before 1900, it was believed that light is an electromagnetic wave consisting of oscillating electric and magnetic field, but in 1900, Max Planck was able to explain the spectrum of blackbody radiation by assuming blackbody walls emit or absorb electromagnetic radiation in units or discrete packets of energy rather than continuous fashion predicted by classical physics. Then, based on his work, Einstein in 1905 explained the phenomena of photoelectric effect by assuming particle or photon nature of light. So today we are going to talk about what is Compton effect, what was the experimental setup, and then we will see the theoretical derivation of Compton effect. So Compton effect, also called the Compton scattering, is the result of collision between the high energy X-ray photons and the free electrons of target material. And in the process of collision, the electron is recoiled and the photon is scattered with a lower energy. Now, let us try to understand the experimental arrangement of Compton scattering and observations obtained from it. So we have X-ray source which emits beam of monochromatic X-rays of wavelength lambda, and it is made to pass through a pair of collimators, and then these X-rays are made to fall on some kind of target material like graphite crystal, and when they interact with the electrons inside the crystal, they get scattered in different directions. Here you can see there is a detector placed behind the target called Bragg's spectrometer, which is capable of measuring the scattered X-rays at different scattering angles. Now, what we observe from this experiment, we get this type of graph. Here x-axis is the wavelength of the scattered X-rays and y-axis represent the intensity of scattered X-rays measured at different scattering angles. For all scattering angles except for angle 0, we get intensity versus wavelength graph associated with two intensity peaks. One peak is located at wavelength lambda, which is the wavelength of the incident beam, and the other peak is located at some other wavelength lambda dash, which has a wavelength greater than that of the incident beam. And the separation between the two peaks is delta lambda, called as Compton shift. Here you can see this difference in wavelength between the two peaks increases with the angle of scattering. So experimentally, we are observing some kind of shift in wavelength between the scattered and the incident radiation. Classical theory was not able to explain this experimental result. In the classical picture, the wavelength of the scattered radiation is expected to be the same as that of the wavelength of incident radiation when X-rays are scattered by some kind of target material. Then Compton in 1923 gave the explanation of the experimental results based on the following assumptions. First, he assumed that X-rays are composed of photons which behaves as particle having energy and momentum, just like what Einstein assumed on the theory of photoelectric effect. Second, since the outer shell electrons of the target atom are loosely bound, so it requires a very small amount of energy to leave the atom. So for high energy X-rays, loosely bound electrons are assumed to be free electrons at rest. Third, the collision between the incident photons and electrons is an elastic collision, just like two particles collide with each other, and in such a collision, energy and momentum will be conserved. So you can see in this diagram, when X-ray photon collide with electron, a part of its energy is imparted to the electron and electron get recoiled with high velocity at angle phi with respect to the incident direction, and the photon get scattered at an angle theta with lower frequency nu dash. That is, during collision, photon transfers some of its energy and momentum to the electron and get scattered with a lesser energy in a particular direction. So in such a collision, there is an exchange of energy and momentum. So let us understand the energy and momentum expression before and after collision. Let incident photon has energy h nu and its momentum is p is equal to h nu over c. And the electron is initially at rest, so its rest mass energy will be m naught c square and its momentum will be 0. Now after collision, the scattered photon has changed frequency. So its energy will be E is equal to h nu dash and its momentum will be P is equal to h nu dash over C. And after collision, the electron has gained some energy. So it has both energy and momentum. So its relativistic energy will be taken as E is equal to P square C square plus m naught square C to the power 4 whole power half. And its momentum is considered as P. Let us consider these expressions and try to apply the law of conservation of energy and momentum. Now let us first apply the conservation of energy. Total energy of incident photon and electron before the collision is equal to total energy of the scattered photon and electron after the collision. That is h nu plus m naught c square is equal to h nu dash plus p square c square plus m naught square c to the power 4 whole power half. And when we simplify this equation, we get the expression p square c square plus m naught square c to the power 4 whole power half is equal to h nu minus nu dash plus m naught c square. And after squaring this equation, we get the expression p square c square plus m naught square c to the power 4 is equal to h nu minus nu dash plus m naught c square whole power 2. And further simplifying this equation, we will achieve equation number 1, that is p square c square over h square is equal to nu minus nu dash whole square plus 2 m naught c square over h nu minus nu dash. Now let us apply the law of conservation of momentum. Since momentum is conserved in two mutually perpendicular directions, so we can take the projection along x-axis and y-axis. In the right hand side of figure, the projection of the term h nu dash over c along x-axis is h nu dash over c cos theta, and along y-axis it is h nu dash over c sin theta. And for the term, its projection along x-axis is p cos phi, and along negative y-axis its projection is minus p sin phi. So you can see in the left hand side of figure, along x-axis before and after collision momentum will be h nu over c plus 0 is equal to h nu over c cos theta plus p cos phi. After simplifying it, we get equation number 2. And along y-axis before collision momentum is 0 for both the photon and electron, but after collision momentum will be h nu dash over c sin theta minus p sin phi, and we get the expression 3. Now after squaring and adding equation 2 and 3, we get p square c square over h square cos square phi plus p square c square over h square sin square phi is equal to nu minus nu dash cos theta whole power 2 plus nu dash square sin square theta. And after simplifying it stepwise, we will achieve equation number 4. Since left hand side of equation 4 and equation number 2 is same, so we can write nu minus nu dash whole power 2 plus 2 m naught c square over h nu minus nu dash is equal to nu minus nu dash whole power 2 plus 2 nu dash 1 minus cos theta. And after simplifying it, we will get equation number 5, that is 1 over nu dash minus 1 over nu is equal to h over m naught c square 1 minus cos theta. And multiplying by c to both sides of equation 5, we will get c over nu dash minus c over nu is equal to h over m naught c 1 minus cos theta. And in terms of wavelength, we can write lambda dash minus lambda is equal to h over m naught c 1 minus cos theta. We can also write delta lambda is equal to lambda dash minus lambda is equal to h over m naught c 1 minus cos theta, where lambda dash is equal to c over nu dash and lambda is equal to c over nu, and delta lambda is equal to lambda dash minus lambda. So we derived the expression for shift in wavelength or Compton shift, that is delta lambda is equal to lambda dash minus lambda is equal to h over m naught c 1 minus cos theta, where lambda is the wavelength of the incident radiation, lambda dash is the wavelength of the scattered radiation, theta is the angle with respect to the incident direction, h is Planck's constant, m naught is mass of electron, and c is the speed of light. Because h, m naught, c are constant. So the factor h over m naught c has a fixed value. And it is called the Compton wavelength of the electron. And it is denoted by lambda c. And its numerical value is equal to 0.0242 angstrom. Now, the expression of delta lambda leads to the following conclusion. The wavelength of the scattered radiation at different angle is always greater than the wavelength of the incident radiation. And the shift in wavelength is independent of the material contained in the target. And it depends only on the scattering angle, theta. Now, let us consider three cases. First, when scattering angle is 0, in this case, Compton shift will be 0. That is, delta lambda is equal to 0, which shows that there is no scattering along the direction of incidence. Second, when the scattering angle is 90, in this case, Compton shift is equal to Compton wavelength, that is equal to the value of lambda c. So, delta lambda is equal to 0.0242 angstrom. Third, when the scattering angle is 180. In this case, Compton shift is equal to 2 times of Compton wavelength. So, delta lambda is equal to 0.0484 angstrom. So, the Compton shift increases with the increase of scattering angle. That is, the maximum value of Compton shift occur for theta is equal to 180 degree. That is, when photon collide with the electron and scattered completely in backward direction. Then we will get maximum value of Compton shift. Hence, the theoretical expression of Compton shift is in good agreement with the experimental results. Now, what will be the effect on Compton shift when a photon strikes an electron tightly bound to the nucleus? Since in the whole discussion, the electron was assumed to be a free electron. But if a photon interacts with a tightly bound electron of the target atom, then electron does not get detached by the impact of the photon, but remains bound to the nucleus. For such a case, photon collide with the entire target atom rather than an isolated electron, and the atom as a whole takes the recoil momentum. So, the equation of the Compton shift get modified as delta lambda is equal to h over mc 1 minus cos theta. Instead of delta lambda is equal to h over m naught c 1 minus cos theta, where m is the mass of the entire target atom, which is much heavier than the mass of the electron. Hence, the Compton shift becomes too small to be neglected, and we get scattered photon of unmodified wavelength only. That is, there will be no change in wavelength, and this is the classical result. Now, experimentally, we are getting two intensity peaks of scattered radiation. First peak is called the unmodified wavelength or Rayleigh line, and it appears due to scattering from a bound electron of the target atom. Whereas second peak is called the modified wavelength or Compton line, occurs due to the scattering from the free electron. So both the phenomena is happening in the Compton effect.